Everyone, Assalamu alaikum. Today we will be discussing anti-arrhythmic drugs. You are quite familiar that anti-arrhythmic drugs are very important in cardiology and medicine. Now, having said that, let me proceed that how these drugs works. Uh, you know, One can say that arrhythmias exist when there is no normal rhythm in the heart, or when the heart deviates from the normal rhythm, one can say that arrhythmias exist. Now, what is the normal rhythm? The question is, so the normal rhythm is that usually human heart beats between 60 to 100 beats per minute, and you can say that this is now normal rhythm. There are certain key characteristics of cardiac myocytes, and you know that there is automaticity, uh, rhythmicity, and conductivity. But automaticity refers to that there is spontaneous generation of currents from the SI nodes, and different vectors are generated, and these different vectors, their algebraic summation is at least to a particular type of vector, and then it is going to repolarize both auricles. You see this one, and once these auricles are repolarized, so it's going to pump the blood into different chambers. For example, it pumps the blood into the ventricles and some of the blood vessels, and keep the hemodynamics in a normal way. But for most of the blood, ventricle is responsible for ejection of blood into the aorta. So it is the ventricle that more than 80% of the blood is ejected because of the ventricular contraction. So ventricle is usually contributing to the pumping phenomena, but it's not so simple. You see, there is AV node, and once these reaches the AV node, so then it stay down. This is why it is called AV node. It is at the atrium ventricular junction. This is very fast generating, and you see where AV nodes are made of specialized cells, and is going to pass the vectors, and it is now modulated here. Modulated mean that it passes very slowly, and since it passes very slowly, so it gives time for the auricles to relax, and the ventricle simultaneously depolarizes. So how it happens, you see, once we talk about automaticity, so it means that there is spontaneous generation of currents from the SI node. This is SI node, you see. And once we talk about conductivity, mean that the impulses are going to travel down through this particular atrioventricular node, going down to this bundle of Hess and Purkinje's fibers. So what happens, you see, once the auricle depolarizes, so a P wave is generated, and then it is followed by a depolarization of bundle of Hess. Remember, it's passing through the atrioventricular node, so it's going to produce a Q waves, and then both the sides are the Purkinje fibers are depolarized. This influx of sodium, and then it leads to the generation of QRS complex, and this is followed by the repolarization phase, and repolarization phase mean this generation of T wave. So you see, the repolarization is very passive phenomena, so thus it takes much more time, and electrocardiogram time is on x-axis, whereas the current is on y-axis. So therefore T wave is starting from here, and it's reaching here because it's going to merge at the isoelectric point. So repolarization is passive phenomena. Thus the key characteristic of a cardiac myocytes are automaticity, rhythmicity, and conductivity, and any abnormalities either in this automaticity will lead to certain disorder like sixth sinus syndrome, or sinus tachyarrhythmia, or sinus bradyarrhythmia, or in case of conductivity it will lead to particular case of heart block like first degree block, second degree block, third degree block, and you see, and then of course ultimately the rhythm will be no longer a normal rhythm, as it is that it beats between 60 to 100 beats per minute. So therefore, these are the three key cardinal characteristics of my cardiac myocytes. So all these things should be within the normal range. Now, as I said, this is once auricle depolarizes, so P wave is generated, and this QRS complex is as a ventricular depolarization waves followed by T wave, that is ventricular repolarization wave. Now, certain condition for normal and abnormal rhythms. So for normal rhythm, as I referred to in the previous slide, that it is between 60 to 100 beats per minute, but these key characteristics are important. Number first one is that every beat should originate from the SA node. All impulses should pass through the normal conduction pathway, that is the AV node, bundle of Hess and Purkinje fibers. And if it is not going to pass through any of this pathway, it means it can create problems for you people, like re-entry phenomena, short circuits, or whatever the case will be. Therefore, normal velocity is also important. Normal velocity mean conductivity is also important, because that will lead to certain arrhythmias. Now, there may be, when the heart rate is below 40 to 60, this is called mild bradyarrhythmia, and same is that is moderate bradyarrhythmia in this particular beats rate, and when it is less than 20 beats per minute, so it's severe bradyarrhythmia and it's an emergency and requires treatment. In case of tachyarrhythmia, you see, usually there are some paroxysmal tachyarrhythmias which usually they are auto-reversed, but in case of simple tachyarrhythmia, you see this is from 101 to 150 beats per minute, and in case of flutters, whether that is atrial flutters or ventricular flutters, you see, so flutters are usually common in atria, so that is called 250 to 350 beats per minute is there, and when it is greater than 350, it is called fibrillation. So now you understand that there is a normal heart rhythm. If it is increased, so it is going to produce tachyarrhythmia, and from this normal, if it is decreased, it is going to produce bradyarrhythmia. Now, if we classify the arrhythmias based on its origin, so you can say that in case of auricles, you see, and then it is followed by the ventricles. So, and this is the junction. So what you can say, SA node and the AV node, then the bundle of Purkinje fibers on either side, you see, and this is how you are going to so what happens when the arrhythmias are in this ventricular walls and originating from any of the myocardial wall somewhere else from here, so then they are called ventricular arrhythmias. But you see, this is the junction, and this junction is these AV nodes. So if it is going to originate from this junctional region, they are called junctional arrhythmias. And if it is through the atrial wall, you see, these are atrial walls. Somewhere else, some region are going to generate some vectors, and these are called, then they are called atrial arrhythmias. And as we discussed that in case of atrial tachycardia, 150 to 250 beats per minute, and in case of flutters, you see, this is 250 to 350 beats per minute, and in case of fibrillation, more than 350 beats per minute. So what is important? This sinus, this is important. Sinus SA node is important, and arrhythmia of sinus origin are called sinus arrhythmias. Remember, sinus tachyarrhythmia. In case of sinus tachyarrhythmia, the heart rate is increased, and you see there may be sinus bradyarrhythmia as well. And there may be a condition which is called as sinus tachyarrhythmia followed by bradyarrhythmia, tachyarrhythmia, bradyarrhythmia, and this is usually called as sick sinus syndrome, or sometimes it is called as a Wolff Parkinson White syndrome. This is important. So you know now classification may be based on origin, and these are called supraventricular tachycardias, and these are sometimes auto reversed. So you see, now if we go uh, uh, how the electrocardiogram is. In case of atrial tachyarrhythmia, P waves are normal, but usually 2, 3, 4 waves appears, and then the Q wave, then the RS complex is there. But in case of atrial flutter, you see is 1, 2, 3, and 4. But this is just like a tooth teeth, like saw, just like saw mean raha. So you see, uh, mm, and because it's not getting much more time, that the P wave should be properly reflected. In case of atrial fibrillation, the P wave just like appearing like dots, you see, and it's not going to going to not going to the vector are not so sufficient to reach here in such particular magnitude. So it is not, the P wave is not represented here, you see. So it's just like what you can say, just like dots are there, then followed by QRS complex. Now let me move to, so usually in case of atrial flutter, this P wave is represented by big capital F, and in case of fibrillation is represented by small f. What is important in this slide, here you can see the action potential, that is a trigger phenomena. So the mechanism involved in the ventricular, in the arrhythmias rather, that is the trigger phenomena may be there, and trigger, you know, there is SI nodes as we discussed in the previous slide, and there is automaticity problem, maybe in the automaticity, and problem maybe in the this pathway, as we discussed, from the SI node it reaches to the AV node. So keep in mind the concept of depolarization and repolarization, as we have uploaded a video on my channel, that is with the name of Professor Dr. Niaz, and you can go and see the concept of depolarization and repolarization, because that is very important to understand the cardiac myocytes. So what is important? Important is that in some cases, in case of trigger, this as the plateau phase is about to finish, so certain area, from certain area, you see other currents are generated, and that's going to produce another small action potential, and this is called as early depolarization arrhythmias. And there may be in the late stage of this depolarization, you see arrhythmias may be there. They are called delayed after depolarization arrhythmia, as usually happens in an ischemic or injured heart, you see, because the heart may be loaded with cations and cyclic AMPs is not degraded, you see. So this will be a different story. But what happens, you see, in case of SI nodal depolarization, when problem is there, so sinus tachycardia, as I discussed, this how you come to know about sinus tachycardia. For example, if this green line of ECG is, this is P wave QRS complex, and then the T wave and the P wave again, and then the QRS complex. So if this is normal RR distance, you see, so what happens in case of sinus tachyarrhythmia? So distance between the P waves is shortened, or you can say a distance between the two R, successive R, is less than the normal. So it means that more number of beats are there. This is called sinus tachyarrhythmia. And in case of sinus arrhythmia, distance between one P wave and the other P wave, you can say that is increased, or distance between two successive R is increased, you can say like that. And this is, then it is called as sinus arrhythmia. And as we discussed in the previous slide, that there may be six sinus syndrome, where the sinus is weak or injured due to any pathological conditions, or any cation loads, or any electrolyte imbalance. And what happens then? There is tachyarrhythmia, and tachyarrhythmia is then followed by bradyarrhythmia. So here this is condition of tachyarrhythmia, you see, distance is very short, and then it is followed by a bradyarrhythmia, you see, a distance between RR that is very long, more than a normal. If this is normal, you see, So this is abnormal shortened wave. This is again shortened into and this is now increased. So this is classical example of sixth sinus syndrome or Wolff-Parkinson White syndrome. Now another important point that is that once it passes through the this AB node, so it's bidirectional, coming here, vectors are coming here, and then it goes to the septal, and once it goes to the septal, it's going to on either side on Purkinje's tissues, and it's going to repolarize. So in case of block, you see what happens. This comes here, it follows this pathway, of course, but it is not going to pass through this pathway. Here is the problem, you see. So it may comes and follow this pathway, but cannot come this through this pathway, as it coming here and here. So this is called as so here the re-entry phenomena is here, and it is now creating problem for you. So this is called circus movement. Or so this mechanism are either due to the automaticity or due to the triggering phenomena or the re-entry phenomena is there. But better, once again, I would suggest that go and see the concept of depolarization and repolarization. This is an action potential of heart, you see. This is a of S4, you see, and the heart myocardium or Purkinje fiber is now going to reach this threshold, and once reaching this threshold, you see it's going to be a sudden influx of sodiums. So phase, this is called zero phase, and this zero phase is called fast upstroke. Why it is called upstroke? It's going in this direction, you see, from this minus 70 millivolt resting membrane. This is RMP, resting membrane potential, and this resting membrane potential is now reaching this threshold. This is the threshold, you see, and reaching the threshold, then it is fired. But there is influx of what you can say sodium. They are very fast channels, and drug like quinidine will block this influx of sodium, you see. So what happens? There is influx of sodium very fast. It happens in fraction of second as time is on x-axis, and the current that is in millivolt is on y-axis. You understand that? So, and when it reaches the maximum values, you see, then it is followed by a partial repolarization wave. And partial repolarization mean wave that it is going in this direction now. It is upsurge, and in case of phase 1, there will be a slight decrease, you see, and this slight decrease is due to the stoppage of sodium influx and then the efflux of potassium. The efflux of potassium, that is what you can say, there is efflux of potassium is there. So if efflux of potassium is there, then it is followed by a phase of plateau phase, you see. This is plateau phase. This is plateau phase. This is usually with the entry of calcium, and just to balance the potassium outward efflux as it happened in this stage. So what happens in this plateau? The calcium gets inside, and once the calcium gets inside, so you see this is a very slow phenomena. So from here, if I draw perpendicular, and from here perpendicular here, so this is going to contribute a lot of time calcium is giving, and that is why the heart rate of the human being is within the on average it beats 70 to 72 beats. With that of experimental animal like rat and mice, it is 350 to 450 beats per minute, because of this period is less. Now this is followed by further repolarization phase. You see, this is repolarization. It's going back down to again to this resting membrane potential, and this is called as repolarization phase, phase 3 or repolarization phase. Calcium channel are opened, you see, potassium efflux starts due to the opening of repolarize the cells, and you see this leads to the imbalance of sodium and potassium. Thus sodium potassium ATPase will come. This is now involvement of the energy, and this involvement of the energy, now the sodium already which influx and initiated in this phase, zero phase, you see, is effluxed out. It is effluxed out through the involvement of energy. In Pashto, somebody says the Zorauru Baba Barazi. So you can say like that, that once energy is involved, it goes against the concentration gradient. Now, what is happening in the next phase, that is phase 4? So reaching this resting membrane potential, now it's going to reach this. This is a particular slope is there, and reaching the threshold, again another action potential is generated. So there are certain drugs. If there is a particular angle between this, you see this makes a particular angle, and if I represent this as angle theta, you see, so drugs which decrease the slope, this slope is if decreased, I will write for you like here, like this one. Decreasing the slope mean that it will now take much more time. You see, it is now taking here and here. Now it touched this threshold. You see, this is the threshold. So there are certain drugs that is going to make a slope of the phase 4 repolarization. This phase 4, there are forward current. So if slope is decreased, mean it will take much more time. First it was going to touch this threshold here at this particular time, as time is on x-axis. Now in presence of certain drugs like quinidine, so it is going to now prolong this time, and delaying this time mean that number of beats per minute now will be decreased. This is how certain drugs is going to manage the tachyarrhythmia as well. So you understand this phenomena, and then it is followed by this influx and efflux of different electrolyte. This current comes to surface and different electrodes are placed, and then it is appeared as electrocardiogram. So what is important? Important this is that you must understand the normal action potential. Now, if we go to certain drugs that is going to affect this particular step as we discussed in the previous slide. So classification of antiarrhythmic drugs is as such. They are placed how? Class 1A, 1B, 1C, or it is followed by class 2, class 3, and class 4 antiarrhythmic drugs. 1 is placed in subcategory A, B, and C. And remember, in both the cases, since these are sodium channel blockers of case 1s, and once these are sodium channel blockers, so keep in mind the class 1A is going to slow the phase, zero phase. This was the zero phase, if you recall your memory, and depolarization is slowed down. You can see this red one, you see. So first if it's going to there, so now it happens in a very fraction short of time. If I draw perpendicular, this is similar one, and here is the time. Now since it is delayed, so if I draw perpendicular from here, so this much time it is now delayed. So what happens? It slows down the zero phase depolarization. In case of 1B, it shortened the phase 3 repolarization, and in case of 1C, it markedly slows the zero phase depolarization. And zero phase, you know, this is markedly means this is a classical difference. If I draw perpendicular from here and perpendicular from here, now you see this difference is very high, you can see, than this particular difference. So that is why they're placed as or classified as marked. And the drugs working here is disopyramide, quinidine, procanamide, and lignocaine, and flecainamide or flecainide, you see. But 1A for that is classical quinidine drugs, and for 1B you can see lignocaine, and for 1C there is a flecainide. And for class 2, if you go there, this is called as beta adrenoreceptor blocking agents like propranolol, enderol, and so many other, metoprolol, carvedilol, esmolol. So they are beta receptor blocking agent, and what they suppresses the zero phase depolarization, and the zero phase suppresses mean that if it is going to slope will be decreased, as I discussed in the previous slide. And decreasing the slope mean that it will now take much more time to reach the threshold, and consequently tachyarrhythmia will be relieved. Beta adrenoreceptor antagonist, and like drug is atenolol and sotalol. Third class is that prolong the action potential and prolong the refractive period. And the third class is going to prolong the refractive period. Refractive period mean if a drug is given and first it is following this pathway, you see, in the presence of drug, this will follow now this pathway like this one. So the refractory period is prolonged. You see now, and then since time is on x-axis, so again number of beats will be decreased. So there, that is how these amiodarone or sotalol. Again, sotalol is the classical drugs. It works as class 2, it works at class 3, and perhaps they are placed as a classical antiarrhythmic drugs. The beauty of God is that quinidine, you see, is isomer of chloroquine. Quinidine is isomer of chloroquine, and both of them have similar molecular weight. But this is the difference between the orientation of the hydroxyl group above the equatorial plate. That one is antiarrhythmic and the other is antimalarial. This is a technical point to remember. And then the phase 4, or you can say calcium channel antagonists like verapamil or diltiazem, they are going to inhibit the calcium influx, and inhibiting the calcium influx, you see, will lead to the delaying of what you can say this action potential, and consequently, as this plateau period will be prolonged, and prolonging this plateau period will again the effective refractory period duration will be prolonged. Consequently, these drugs will work as antiarrhythmic drugs. Now, I hope you understand that how antiarrhythmic drugs works and what particular you can see the manifestation will be in the electrocardiogram. So they are used for different therapeutic purposes, as the name indicates, like calcium channel blockers. They are anti-anginas, antiarrhythmic, antihypertensive, vasodilators, Raynaud's phenomena, and primary hypertensions. You see, cardia, atrial flutter, and atrial fibrillation. So I hope you understand, and now you go and make a table of these particular classes of drugs. You can see, and making these class of drugs. Now remember its dose, and dosimetry, frequency, as well as half-life and adverse effects.